In today's lectures, you are going to study the electric potential. First topic is the electric potential energy. Second topic is the electric potential. Last topic is the potential gradient. First topic is the electric potential energy. In daily life, we have many chances to use energies. So when you study the Introduction to Physical Sciences, you study the mechanics. In mechanics, we consider the gravitational potential energy due to gravities. In the case of the electricity, we consider electric potential energy. So we'd like to derive the expression for the electric potential energy today. First of all, we'd like to review the gravitational potential energy. If we consider the ball at the position of the height is the h, compared with the reference point of 0, gravitational potential energy is expressed mgh. M is the mass of the ball. G is gravitational accelerations. H is the height. A ball in the high position has the gravitational potential energy. When it is dropped, it loses the gravitational potential energies and gains the kinetic energies. So how to calculate these potential energies? So in this case, we consider the ball, gravity acting in a ball. The magnitude of the gravity is expressed as mass and gravitational acceleration, g. Then we'd like to move this ball up to the height of the y equal h. We'd like to move this ball from the y equal 0 up to the y equal h. For the movement, we need to apply force to a ball. Exactly same magnitude of the force of the mg is applied to this ball. Then this ball does not gain velocities. This ball can keep moving with a constant speed from the y equal 0 to the y equal h. So external force equal to the gravitational force is applied to an object. The object moves in the length of h. Then potential energy is calculated by the work. How much work is required to move this object from the initial point to the end point. So applied force is expressed mg. To calculate work, you need to multiply the distance, h. So mg times h gives us the expression for the potential energy. This is how to get the expression for the gravitational potential energy. We use the same method to find the electric potential energy. We consider the two plates. One of the plate has a positive charge and the other plate has a negative charge. Then we can create the uniform electric field of E between the two plates. This is the uniform electric field. In this case, Q is positive. Then electric force of the QE is acting on the discharge directed downward direction from the positive plate to the negative plate. We'd like to find out the electric potential. To calculate the electric potential, you need to consider the external force to move the object. So applied force is exactly same with the electric force of the QE. We apply the force of the QE to move this object from the y equal 0 to y equal a. Apply the force QE times y. You can calculate electric potential energy in a uniform electric field. Electric potential energy of two charges. So we consider the charge of the Q and the Q sub 0. And we'd like to find out the electric potential energy when the distance between the two charges is a. When these two charges, Q sub 0 becomes at this point. What is the electric field between these two charges? So we choose the reference point. Standard method to choose the electric potential energy is chosen as it becomes 0 when two charges are infinitely far apart. So this means R equals infinite, U is 0. Then force acting between the two charges is expressed 1 over 4 pi epsilon naught times Q sub 0 Q over R squares, following the inverse square laws. We need an external force whose magnitude is exactly same with the electric force. This is electric force. But direction is opposite direction. We need a negative sign. Apply the force change depending on the position. This is the force times distance. So this expression can be expressed with the integrals. Because the sigma delta E is expressed as integral dr. This is how to convert from the sigma to the integral using the Riemann sum. If we perform these integrals, this becomes 1 over 4 pi epsilon naught q sub 0 q over r infinity to the a. It becomes 1 over 4 pi epsilon naught q sub 0 q over a. So this is the electric potential energy of two charges. The electric potential energy of the two charges is depend on the product of the q and q sub 0. If this product becomes positive, electric potential energy is always positive quantities. If the two charges cross, potential energy becomes high compared with the two charges far apart. If the one of the charge of the, for example, q is positive, q sub 0 is negative, product becomes a negative quantities. If the two charge close, potential energy becomes really low compared with if the two charges far apart. Electric potential energy with charge, we consider the q sub 0, q sub 1 and q sub 2 and q sub 3. We'd like to find the potential energy associated with the charge of the q sub 0. Sum up the each potential energy due to the q sub 1, q sub 2 and q sub 3 and expressed with the sigma. The total potential energy is easily calculated because they are scalar quantities. In the case of the electric field, you have to consider the component of the electric field. We need to consider the three components, x component, y component, g component. It's a little bit complicated to calculate. But in the case of the potential energy, it's a scalar quantity. We don't have to consider the directions. We just easily sum up to find out the total potential energy. So even if we consider the total potential energy of these systems, in this case, you need to consider this potential energy between the q sub 1 and q sub 3 and q sub 2, q sub 3 and q sub 1, q sub 2. We can easily calculate by summing up each terms expressed this one. Electric dipole in an electric field, uniform electric field. We consider that this is uniform. So E is a constant quantity. We consider the electric dipole in a uniform electric field. Force of the QE is acting on this positive charge. Electric force of the QE is acting on the negative charge. These two forces of the QE have the same magnitude, but directed in the opposite direction. If you sum up these two forces, actually net force on the electric dipole is 0. It becomes 0. So this dipole does not move in a positive direction or negative directions, but it is going to rotate. So this dipole is going to be rotate in these directions. So we could calculate the torque acting on the dipole with respect to the center of the dipole. If you consider this is centers, so this is d over 2. This is d over 2 because the length between the two charges is a d. So P actually the QD. Then calculate torque acting on the electric dipole. So d over 2 times the force acting on the positive charge. And d over 2 is the length between the center of the electric dipole to the negative charge times force acting on the negative charge. You need to multiply sine phi. Sine phi is between the direction of the P and the direction of the E. This is sine phi. F sub plus F sub minus is QE. You substitute, it becomes QDE sine phi. And the QD is a P. So it becomes PE sine phi. So you can express these quantities using the vector product. This is vector product. So tau equal P cross E. The potential energy of the electric dipole. electric dipole moment is expressed as Q times D. D is the distance between the two charges. We'd like to change the direction of the electric dipole by applying the force onto the electric dipole. If we consider this is the axis of the rotation, this point is the axis of rotation. The electric force is acting on the positive charge in these directions. We just only consider the component of the electric force acting on the electric dipole to make the electric dipole to rotate around the axis of the rotation. This is the minus QE sine phi, because this is phi. And as I explained, we need to apply the external force of the same magnitude of the QE sine phi in the opposite directions to rotate this electric dipole with the length of the d sine phi. This is the length. So d sine phi, d is the distance between the two charges. Delta phi, the change of the phi, is small compared with the phi. You could calculate the length can be expressed as d delta phi. Then potential energy is chosen as it becomes zero when dipole moment is perpendicular to the electric field. So this is the electric field. If the electric dipole moment is here, U is 0. So we choose a reference point. Then we'd like to calculate electric potential, electric dipole. So this is the applied force, external force, times distance to find out work done by the external force. Then expressed with the integral. You can easily integrate. This becomes minus QE cosine phi times d pi over 2 phi. You can come to this equations if you use a P equal QD. PE cosine phi can be expressed with a scalar product P dot E. I have shown you how to calculate the potential energy of an electric dipole in these lectures.